margin
Okay,
fast.
so we begin. We have 3 snails. Snail A, and I will not try to draw the snail. Snail A, snail B, and snail C. And they are equal distance apart because they're on an equilateral triangle. And I label the snails. So let's call this distance L, and they're all the same. It's an equilateral triangle. So A begins to move toward B, and B begins to move toward C, and C toward A. And they all have the same velocity. Let's call the velocity V. And do note that the velocity is related to the distance traveled. So the velocity could be written as dl over dt, the change in the space over the change in time. Okay, now the key to this problem is the velocity, or the direction that the snails are traveling, is constantly changing. So as snail B moves to the right, the trajectory of snail A changes. And likewise snail B changes, and likewise snail C changes. So with time, they do indeed form a spiral, and I'm going to sketch one, although this may not be the correct spiral. So the intuition tells you that, hey, they're converging on this point in the center. Okay, so in order to think about this problem, it's best to focus on one region. Let's just focus on this area here. So I'll go to a new space here. Okay, so this is the vertex
and B, and here's the center of the triangle that lies at distance r from A. Let's call this big R the initial radius. In the radial direction, label this radial direction little r, and we're going to solve in polar coordinates, so we'll have the polar coordinate be the theta symbol. So at a small time step, the A moves toward B a distance dl, and if we consider how much the radius is reduced in this small time step, we write dl, and it's dl times the cosine of alpha, where alpha is pi over 6. So then in this small time step, the distance that r is reduced is d little r, and this is minus dl times the cosine of alpha, and we can rewrite this as minus v dt using the velocity distance relationship. So the next step is to integrate this equation, because we really want to know how long it takes the radius to become 0. So we set up an integral, and the limits are the key here. The limits on the right-hand side goes from 0 to tf integrated with dt, where tf is the final time. And on the left-hand side, the radius at time equals 0 is r, and at time equals tf it's 0. And then we solve this integral, moving a minus sign to the other side. We're left with big R equals v. We pull the cosine of alpha, a constant, out of the integral. So v times the cosine of alpha times t, or tf. And r, we then just realize the cosine of alpha is the square root of 3 over 2 times time. Okay, so now that we have a relationship between r and t, we need to change this to a relationship between L and T. So r can be related to L by noting that there's a 90-degree triangle inside of the equilateral triangle. So note the cosine of 30 degrees is the square root of 3 over 2. Making this substitution, we're left with r equals L over the square root of 3. And now we can solve our earlier equation for time, 2r over v times the square root of 3, and make our substitution, and we're left with t equals 2/3 L over v. And that is the answer to the first problem. What is a little interesting to note is that the radius of each A, B, and C is decreasing towards 0. And since the velocity is the same, and the vector takes the same angle, the rate of decrease is always the same. So this problem was pretty simple. Now the second problem, we need to calculate the theta component. And we would like to know how theta changes with time. So over the small differential time, the theta component changes by dl times the sine of pi over 6. Now note that the theta direction is perpendicular to r, and we can use this fact by building a right triangle with a height dl times the sine of alpha that is opposite to theta, and if theta is small enough, the height is also just r d theta. So then we substitute in our velocity expression. We realize that the sine of 30 degrees is 1/2, so we're left with v dt times 1/2 is r d theta. Now little r depends on t, but we've already solved that problem in part 1. So making that substitution, we're left with this expression v over 2 dt is r minus v root 3 times t over 2 times d theta. And this is a differential equation. We write this as d theta over dt, and then we separate variables and integrate both sides. And I won't go over those details. And then the final expression is theta as a function of time. And we can check our expression by looking at the case when the time is 0. We had better see that the theta is 0. And when the time goes to 2L divided by V times 3, my expression is actually wrong in the drawing there. It should be 2L over 3V. Then we note that the theta goes to infinity. So this says as the snails get closer and closer together, they spin around